All right, so according to Transport Canada, about 750,000 medium and heavy trucks transport goods across Canada today. Most of these use diesel fuel, contributing ultimately to poor air quality and pollution. Replacing just a fraction of these with an alternate fuel could have a huge impact. So today, our class will explore the study of a small-scale dimethyl ether production facility. DME is a good option as it has a low particulate emissions and is sulfur-free. It is a promising future energy source.
All right, so to appropriately design the small-scale dimethyl ether production facility, a number of business objectives must be met. Firstly, the feed package must consist of enough information to support the economic risk analysis with a plus or minus 25% accuracy of capital costs. Furthermore, the incentives of the design must be included in the economic analysis and the price of the green fuel to make the process economical. So this must be explored. The facility must be sized with a production rate to accommodate roughly 100 trucks, consuming 50 metric tons of DME per year. The plant's design must be able to be replicated in multiple locations across Canada, with consistent products being produced in each plant. And finally, the resultant product must meet the ASTM fuel grade standard of DME, which has a mass percent of 99.85.
After completing an environmental and economic analysis of the plant itself, it was determined that although the plant is environmentally beneficial, it is not economically feasible. As a result, it is not recommended to go forward with this plant, and we're going to explain to you during this presentation why. And basically, the reason behind that is that the initial capital cost is too high and is not offset by the revenue generated by producing the DME and using that instead of diesel.
The following figure shows the design process that was used to determine if the project was feasible. Each of these steps will be explained in more detail. However, basically we started off by looking at the background information about pre-existing plants that are used in industry, as well as different types of catalysts available for the dehydration reaction. And from there, we examined two types of catalysts and chose one of those catalysts to carry on with the simulation of and develop the process. And once we had that process developed, we looked at the equipment sizing, the optimization, and the materials of construction. And once we had sized all the equipment, we decided on what control mechanisms we would use to control the process. And afterwards that, we looked at the environmental and economic feasibility of the project.
So shown here is our Google SketchUp 3D model of an example plant that's going to be located in Kingston. You can see over on the right side, there's the methanol storage tanks. And over on the far left side is where the DME tanks are kept. And in the middle is where the production facility is. And you can see inside this box, it's small enough to fit inside a shipping container so that it can be as portable as possible, as described in the business objectives. So the process feeds in from the right and then eventually goes out to the columns over on the left. So these columns are very tall and thin. They would be transported on top of transport trucks in pieces. And then in the background, you can see the fueling station where the trucks would be coming in off the highway to fill up their DME tanks.
So one of the first things we considered in our design process was the actual chemistry behind the process. So how we're actually going to be doing this is by doing a methanol dehydration, which is acid catalyzed. As you can see here, that's the process that we're going to be using. And one of the problems is that it creates water as a byproduct. And this is a problem because water has an inhibitory effect on both of the catalysts that we consider during this process. And what this means is that how the reaction actually works is it takes place on the surface of the catalyst when the methanol adsorbs to the catalyst. But the problem is that water can have this same interaction with the catalyst. It can bind to the catalyst, preventing methanol from being able to bind. And that therefore decreases the kinetics of our reaction. So one thing we're going to be looking at and talking about is the possibility of an alternative catalyst, which Kyle will be talking about later. We also determined that we could have a liquid or gas reaction feasible with this process. So the two catalysts that we considered based on the amount of literature available for each were the Amberlist 35, which is a super acid resin, and this is more suitable for low temperature applications, and then gamma alumina oxide, which is more suitable for high temperature applications. So the next phase of our design was to compare these two catalysts and do an analysis on which one we think would be better, and thereby determining whether we'd be doing a high temperature or low temperature process.
So here's a quick pug chart underlying the differences between the two catalyst designs. So since our process is exothermic, the gamma alumina oxide catalyst will have a higher reaction rate since it's be operating at a higher temperature. The selectivity, while minor, is slightly higher for the low temperature model, along with the yield, since at a higher temperature you'll have a lower equilibrium constant. The operational cost of the gamma alumina oxide catalyst will be slightly larger due to the higher temperature and heating requirements involved, while there's a lower capital cost involved with it due to the lower number of unit operations. Now, when we're trying to begin, we reviewed and researched a couple papers to examine the applicability for both catalysts. We collected several papers and reviewed the operating conditions, kinetic results, and assumptions made in each paper. Unfortunately, we found a lot of discrepancies between the papers when comparing final rate expressions, so we unfortunately did derive our own. So we began our derivation by examining a temperature versus reactor length plot for the high temperature catalyst. We made the assumption that at the very start of the reaction, the methanol mole concentration would be approximately equal to 1, which reduced our final rate expression. From there, we recreated the packed bed reactor in Aspen HYSYS and constructed an Arrhenius plot by taking two data points as seen at the very start of the reaction. And by doing this, we were able to determine our pre-exponential factor and our activation energy. And we combined these two pieces of data with an approximation of the equilibrium constant. And by finding all these pieces of information, we were able to determine our heterogeneous catalyst rate expression. And so in HYSYS, as you can see on the right, that's our final temperature plot in HYSYS. And when comparing it to the literature data, we can see there's an accurate fit to the data, which essentially validates our model and it allows us to carry on with our design.
So as Beth had previously mentioned, we had looked at the Amylase 35 catalyst as well as the gamma aluminum oxide catalyst, which both had the competitive inhibition properties with the product water. So we're looking at another type of catalyst called HGSM5, which is actually a hydrophobic catalyst and will prevent the inhibitory effects of water on the methanol dehydration reaction. So it'll increase the kinetics and will likely decrease the size, temperature, and pressure of the reaction vessel. Unfortunately, it was out of the scope of our work, so we didn't do too much analysis on the actual kinetics. So right now we're going to move into looking over the process itself.
So you can now see, just trying to find my mouse here. Okay, so going to do this with the mouse here. So if you follow the mouse, you'll be able to follow what I'm telling you on the screen. So right here we have our methanol storage system. And what happens here is we have methanol product, and we looked at the data sheets on the Methanex website to figure out what type of impurities we could expect in our methanol. And then the methanol comes up, goes into a feed pump right here, and that gets it up to pressure to push it through the system, and it meets up right here with the recycle stream that comes out the bottom of the second column, and I'll get to that later. So what's happening now is the methanol is going to come through a couple of heat exchangers, and it will be vaporized in this process as it makes its way into the reactor. So at the reactor, it's almost 100% methanol, it's 350 degrees Celsius, and it's a pure vapor. After the reactor, we can achieve a 70% conversion on one pass, and the temperature rises to about 450 degrees Celsius. At this point, we have a mixture of dimethyl ether, a little bit of unreacted methanol, and water. Now we go back through and we pass it through a couple of heat exchangers, one of them right here, and another one right here to remove excess heat from the stream. After the second heat exchanger, it partially condenses, so we send it into a knockout drum, and that separates the vapor from the liquid stream. After the knockout drum, it gets fed into the first distillation column in two separate streams to increase the column efficiency. This column was optimized around the bottom of the column where the water product's coming off so we could meet our environmental regulations. Off the top of the column, you have a mixture of DME and methanol, which gets fed into a second column. This column here was optimized around the top of the column, which is our DMEs, which goes to the DME storage tanks. So going out the bottom of the column, we have the leftover methanol that wasn't reacted on the reactor. Off of this one here, we're taking a slight purge stream just to prevent the buildup of impurities in our process, and then the remainder is recycled all the way back around to the feed stream. So we did all of our modeling in a process called, or in a program called Aspen HYSYS, and we relied on it pretty heavily, but we tried to validate any numbers they gave us whenever possible, so we weren't just relying on a computer program, but we were actually getting results that we could justify.
So in terms of heat recovery for the process, our heat exchanger network ended up going through a series of revisions, but we ended up using 3 different heat exchangers. We also have one heater, which is just before the reactor. It's only used during startup, so it's used to increase the temperature of the reactants as it goes into the reactor. We also have one cooler, and it's used to decrease the temperature of the process wastewater as it exits the process into the sewer or the environment. And then, so the benefit of using these different heat exchangers would just be to lower the utility cost, which makes the project more economically feasible.
So the next thing we looked at was our control schemes. So we drew process instrumentation diagrams for each one. So I'm just going to talk about a couple important aspects of that. So we used a cascade loop for most of our control systems where we had a control valve with a flow controller. So right here for sheet 1, we have the methanol storage tank. The low level indicator controller will cause the pumps to automatically shut off. So this interlock system will help not starve the pumps. So then from there, our reactor sheet, we included a bypass from the reactor cooler. So if the products come out of the reactor too hot, they will bypass the heat exchanger, and therefore the reactants won't be too hot going into the reactor. So this is our knockout drum P&ID as well. And then from there, our distillation columns, we used a important control system for the wastewater going to the environment. So we included an online analyzer as well as pressure and temperature to control the composition leaving the column. And we used a similar one for the DME, where we controlled with an online analyzer the DME product going to the storage tanks. So lastly, for our storage tanks, we used a high-level indicator with an interlock system to shut off the valve going into the tanks to prevent any overflow.
So in regards to process safety, we used a process hazard analysis using 2 methods, a what-if method and a HAZOP to evaluate the hazards within our facility. Using both methods, we came up with a consequence rating based on the severity of a hazard occurring as well as the likelihood of that hazard occurring. And based on those 2 ratings, that gave us a risk rating. And depending whether or not that risk rating was above our level of acceptable risk, we had to implement further mitigation, which led to a lot of the controls and bypasses that Liz just talked about. In terms of inherent safety of our plant is a small-scale pilot-sized plant, so it is more inherently safe than a large industrial application plant. In addition, as you're about to hear, we have incorporated 2 of our process units into 1 unit. We combine the methanol evaporator and the process coil to form 1 unit, which in turn makes our process more inherently safe.
One of the most efficient ways of reducing capital costs and manufacturing One of the most efficient ways of reducing the capital costs and manufacturing costs of a process is making sure that the materials of construction are able to withstand any inherent corrosiveness present within the process. Luckily for us, the majority of our chemicals and compounds present within the streams are non-corrosive, and so in most cases, carbon steel was deemed adequate for most piping and unit operations. A few select heat exchangers, specifically the tubes within the heat exchangers, were deemed necessary to be made out of austenitic stainless steel or duplex stainless steel to ensure that there was no erosion or corrosion caused by water, being specifically utility water, above 50 degrees C, or high speeds caused by velocities of the liquids within these tubes.
Okay, so next we wanted to optimize the two columns that we have, the DME column and the water column, on a cost basis. So we started by optimizing them from an operations standpoint. So that was done by varying the feed tray. So we just started from the middle and basically worked our way up and down, looking at the reboiler and the condenser duties total, and then costing them and trying to minimize that. It was a bit different for the two columns since the water column had two feeds coming from the knockout drum, whereas the DME column just had the one. After that, we wanted to then minimize the capital cost as well, which is just basically based on the total number of trays, obviously with an increased amount of materials. So we wanted to minimize the number of trays total while also making sure that our operating costs were kept at a minimum. And that's basically all we did.
In terms of vessel sizing throughout the process, we were required to size both the methanol and the DME storage tanks, as well as the reflux drums, the reactor, and finally the knockout drum. In terms of the methanol storage tanks, we considered both the maximum and the minimum delivery time to the facility. In terms of the maximum delivery time, we wanted to ensure that we had enough methanol stored on site so that if delivery took the maximum length of time, we could still maintain production and keep producing DME. Additionally, in terms of the minimum delivery time to the site, we wanted to ensure that if our tanks had methanol in them and we received another methanol shipment in the minimum delivery time, we did not overflow our tanks. For the DME storage tank, we wanted to ensure that if there was ever an error throughout the process that required shutdown, that we had some methanol or DME stockpiled on site to keep supplying the trucks with fuel. So for this, we considered a 5-day stockpile time. For the reflux drums, we placed these following the condensers at both the water and the DME columns. So to size these, we wanted to ensure that we were keeping our liquid seals on the pumps following these. So we considered a 5-minute hold-up time and the mass flow rates to determine the overall size of the reflux drums. For reactor sizing, we assumed that the lengths and diameters provided by the HYSYS model were accurate, and then simply added the wall thickness to the reactor dimensions. And then finally, for the knockout drum, we began sizing assuming that we were using a demister and finding empirical data combined with the liquid parameters provided by HYSYS to overall size the length and diameter of the knockout drum. From this iteration, we found that we had a very small diameter and a very large length. So we removed the demister and subsequently resized our knockout drum to provide a more appropriate length over diameter ratio of closer to 3.
So the next thing that we had to size were, as previously mentioned, there was 8 heat exchangers. So these heat exchangers varied from either a shell and tube, a hybrid design that we'll get into a little bit later, and plate and frame, heat exchangers. And we used 3 different methods to size these heat exchangers. And as you can see, there were the quick sizing method, the steady state rating, and the Aspen exchange design and rating, or EDR method. So the quick sizing method was a really simple calculation that involved pulling values from HYSYS for the flow rates, and then after a series of equations, we got a required area, which we then used to find what appropriate heat exchanger we needed. For the shell and tube heat exchangers, we had to choose what TEMA types we were using, so we had to learn a lot about that, and also a few basic designs, such as which side to put which fluid. And we used a steady state rating for some of those, and that involved first quick sizing the heat exchanger, and then inputting that area into HYSYS, and then varying the parameters until we received what we deemed was an optimized model. The final way of sizing was the EDR method, and that there was just putting in a few basic information into HYSYS, and then using the simulation software to size the equipment for us. So the next step was what we like to call process intensification, and that was when we combined when we designed the methanol evaporator by combining 2 separate heat exchangers. So this is one of the designs that we had, and it's a modified Kettle reboiler. And in this design here, the methanol comes in from, I guess I'll take the mouse. Okay, I don't know where the mouse is, so never mind. So the methanol would come in from the liquid methanol in and flow down to the reactor effluent, and that there is simply a shell and tube heat exchanger, which would partially vaporize the methanol, which then leaves on the top right side of the vaporized methanol area. And when the methanol would reach a point when there's too much methanol within that system, it would overflow over top of the weir to where utility steam would be used to vaporize the rest of the methanol. So this was advantageous because it minimized the amount of steam that was required to achieve the vaporized methanol and made it a more economical product.
The second process intensification design that was developed was nicknamed the Bodlinator by its inventor, Michael Bodley. As you can see, one of the main differences was the incorporation of a knockout drum between two shell and tube heat exchangers. The way that this unit operation works is liquid cool methanol feed is fed into the bottom of the left-hand side of the first shell and tube heat exchanger, and as the liquid levels rise and some of it is vaporized due to the heat transfer between the reactor effluent and this cooled process, the vapor liquid biphasic system comes out of the top, comes into contact with that baffle, and that top weir is meshed, which allows vapor to disengage from the liquid and flow out the top, whereas the liquid itself is drained out into the bottom of the second shell and tube heat exchanger, which vaporizes approximately 25% of it by pass using medium pressure steam. Again, as the liquid levels rise and the vapor rises, it again reaches another baffle and is disengaged using a mesh layer that further allows more vapor to come out the top. One of the main advantages of this system is the fact that there is a recycle incorporated into it, which helps improve efficiency and increases heat transfer rates.
So the third design in our process intensification step was the vertical dual methanol vaporizer. And as you can see here, this is essentially just two shell and tube heat exchangers stacked vertically on top of one another. The methanol reactant comes in at the bottom and travels up, and as it vaporizes and liquid levels rise, travels up through the first heat exchanger where it's heated with the hot product effluent from the reactor. It then travels into the second heat exchanger, which is then heated with utility steam. You'll also note the fairly thick baffle that separates the two heat exchangers, and this is used to prevent heat transfer between the vaporized methanol in the second exchanger and the liquid in the first exchanger.
Okay, so for pricing the entire plant, we used a Chemicon Excel file where we could input all of the equipment that we have within the plant, and then it takes into account a variety of factors like material costs, piping, installation costs, labor costs, and a variety of different things. And from there, it basically just gives us the total cost of everything and sums it up for us. We can also include different things like utilities, raw materials, and pretty much any factor that we can think of in order to get a total cost overall. Yeah.
Okay, so continuing using that Chemicon tool, another one of its functions is it also calculates the profitability of the plant for us. So on this diagram here, we've indicated the annual operating profit and the cumulative discounted cash flow of the plant, and as you can see, they're both negative. The plant operates at a deficit, so its operational costs are quite larger than the revenue it makes from selling DME, and so we see a increasingly decreasing cumulative discounted cash flow. Just a quick overview of the operating costs that this plant incurs. I've highlighted the largest one out of the range, which by far seems to be the raw material cost of methanol. And then if we were going to make this plant profitable, we would have to mitigate that somehow. So one proposed solution was including a methanol plant with this DME plant. On the small scale, we referenced a Methanex plant in Louisiana and scaled it down using a scaling factor method to the same level as the DME plant that we've designed. And it looks like at the small scale, this plant still is not profitable, pushing the NPV even further into the negative. However, on the large scale, it seems to be significantly more profitable. We referenced a plant in Japan by Fuel DME, and it seems that once the capacity reaches somewhere in the range of 446,000 megatons of diesel equivalent. So that number is scaled down from the actual DME output to equivalent so that the price would represent what we're selling DME at as a replacement for diesel. And it's at this scale, the plant becomes significantly more profitable, producing an IRR of 30% and an NPV of about 650 million. Just looking at how sensitive and the risk associated with the plant, the plants depend very heavily on the sales revenue generated. So the price of diesel influences how profitable the plant will be significantly. This is shown by the large bar in the tornado plot on the left. It's also heavily influenced by capital costs and raw materials, since methanol's quite a large operating expense in the small-scale DME plant, and also the percent probability of a profitable plant is 100% in this case, since the NPV is extremely negative. But looking at the larger scale plant, we see that sales revenue is still a large contributing factor to a positive NPV. So any significant change in price could push this plant into a risk of not profitability. The range of capital cost has also been increased since the plant was costed using a scaling method instead of actual design. However, despite these two factors, Chemicon has quoted the probability of profitability at about 82%, with an 18% chance of reaching an NPV less than 0. So, good chances. Some risk is associated with the design that we finished. The methanol, there's some equipment that hasn't really been tested and could account for a large jump in capital, namely the methanol evaporator. Also, the plant is significantly susceptible to impurities. Peroxides can rapidly degrade and cause levies and explosions within the system that could cause serious damage. And despite the engineering that we have completed so far, we haven't gone through any design review or design iteration, received vendor quotes. We still have a lot of estimates to make with civil and electrical engineering, building design, as well as more research into the development required. And we need more site information about real estate costs and the infrastructure that we're building on. So we estimate that the cost growth ratio for this plant would be approximately 74.64%, leaving our final capital estimate at about 7.5 million.
So we've already mentioned the potential benefits of using DME instead of diesel as a fuel source. And now I'm going to talk about 3 factors that influence the environmental impact of our design. So the first one is water. The water is a byproduct of the methanol dehydration used to form DME. So shown in this picture above is the bottom of the water column. This distills the water from the methanol and the DME. And the way we are controlling the composition and temperature of the water is through a control system. So we have a concentration analyzer, which is measuring the concentration of methanol and DME in the water stream leaving the column. And if the concentration of methanol and DME is too high, the flow rate of steam entering the reboiler will increase, therefore decreasing the amount of methanol and DME in the stream. So in this way, the concentration of methanol and DME that's leaving the water column is not a huge environmental factor that needs to be considered. The second environmental factor is noise. The pumps that we have in the design, as well as the 2 reboilers for the columns, will emit a certain amount of noise. Shown in the picture above is the plant, which is labeled by a red star, and then the 4 nearest neighbors, which are of concern. So the first one is a motel, followed by a gas station, a arena, which is called the Invista Center, and then a residential area. Because the plant is on such a small scale and the nearest neighbors are so far away, we determined that noise was also not a significant environmental factor. However, when applying for an environmental compliance approval, an official noise test will need to be completed in order to ensure this. The last is air. Though the plant was not designed to have any consistent air emissions, we do have relief valves on a lot of our vessels that can be isolated. So in this way, if a relief valve were to open due to overpressurization of the vessels, processed material would be released into the air. However, we do have control systems to mitigate this. So shown in the picture is the water column again. In this way, the pressure in the column is controlled by the reflux flow rate of liquid returning back to the column. So if the pressure in the column is too high, the flow rate of liquid will increase, thereby cooling the contents of the column and lowering the pressure. So because we're already controlling the pressure in the column, the relief valve will not need to open except in extreme circumstances. So again, this environmental factor has a low impact.
So to help us in our recommendation whether to move forward with this plant, we also assess sustainability and life cycle of the proposal. So we started by looking at the 4 pillars of sustainability as identified by the City of Kingston. So the pillars being economic, environmental, social, and cultural sustainability. We then moved on to evaluating a life cycle analysis by compiling a list of relevant factors, which include materials that are used in the process, materials that are produced in the process, construction of the plant, and other elements like that. Then we evaluated the potential impacts of these individual factors and interpreted the results to provide a recommendation based on the life cycle estimated through this qualitative assessment. This would be an iterative process if we were to move forward and improve on the sustainability of the plant. So we took the results of this life cycle analysis and placed it into a weighted pro and con table. This is just a sample of the overall table. We sorted the factors into categories based on the 4 pillars of sustainability and compared the number of pros and cons and the relative value of each of them. So for example, some of the pros have to do with DME being a clean burning fuel alternative. However, some of the cons for environmental sustainability have to do with the production of methanol and transport of methanol as well. So based on this qualitative assessment, it does suggest that the life cycle of this plant is sustainable. However, we haven't looked at the quantitative values of these sustainability factors, and that could be an impact moving forward with the plant.
So we're just going to briefly review and wrap up. So for our current design, there are a number of strengths and weaknesses associated with the plant. There's a positive environmental impact due to the reduced particulate emissions of using DME. There's also the added benefit of it being small and easily transportable, which would allow it to be implemented in more remote and isolated areas. There's also an inherent safety, and this was touched on earlier. The plant is, because it is on such a small scale, it's inherently safer than a large plant. Some weaknesses have also been identified. Earlier in the presentation, we discussed the kinetics. There was a number of assumptions made in terms of moving forward with the design, and these would need to be reviewed before the plant could be implemented and alternative methods considered. The large columns also limit the transportation. Everything else is very small scale, but they may present a challenge in moving further towards isolated areas. And as was summarized before, it's not right now economically feasible, and therefore is not ready for implementation, and further research would have to be conducted on alternatives. For the current design, some recommendations for improving it would be implementing it in northern areas or isolated mine sites. In these regions, the cost of fuel tends to be higher. That can be seen in the map of Canada there. Red shows areas of high-costing fuel, orange in the middle, and green and yellow are lower-priced areas. So if we could explore options of implementing this in the northern regions, it would may be more profitable. However, as it stands, the cost of diesel is not high enough in those areas to make this economical yet. However, if those prices continue to rise, there would be other factors to consider, such as transporting the methanol up north would also increase the price, as well as setting up the design and the operational costs. We could also, if the price of diesel were to increase and the price of methanol to decrease, creating a larger gap between the two, we could potentially move forward with this design. Alternative processes could also be considered, so significant scale-up may make the process profitable, as well as looking for ways of producing both methanol and DME, and using syngas as a potential starting material. So thank you everyone for coming out today. A special thank you to GV Energy and Methanex, Greg Rogers and Eric Schweizer for your support throughout the process. And of course, a special thanks to Dave Modi and our tireless TAs for seeing us through the past 3 months. Does anyone have any questions?
Okay, does anybody have any questions for the students?
Yeah, Jason Chesko from Methanex here. Could you firstly clarify the assumptions you used for methanol pricing and DME pricing, and how you arrived at those?
Who wants to answer that? Liam? Okay, let me just drag him down here. He's coming.
So the current methanol prices were taken from the Methanex website for the non-discounted price, which was listed at $475 per metric ton. So that was the number that we had used when pricing our raw materials cost based on the mass flow rates that we needed for our process to run to meet the target. In terms of the DME price, we didn't price what the DME would need to be sold at. We instead looked at the current diesel prices that were being offered in the area, as this project was mainly focused on savings directed towards the company as opposed to generating revenue. So we compared the current price of diesel after going through an energy conversion, assuming that the amount of DME in terms of megajoules would be equivalent to the amount of diesel needed in terms of megajoules. Unfortunately, one of the biggest hurdles was that diesel is just more efficient in terms of its exergy, which meant that any DME produced would have to be in larger quantities than the diesel equivalent, which further increased the methanol price in terms of purchasing the raw material as opposed to the diesel price. I hope that answered your question.
Thank you.
Any more questions?
Gone tough. I'm curious if you thought of any of the experience curve issues that you developed, some of the smaller scale equipment, so that as you replicated this, some of that cost may come down.
Don, can you just say that again? We heard the smaller scale equipment.
Just wondering if you've looked at experience curve implications of replicating your design. So as you made more of them, some of the equipment should come down in cost. Did you explore that at all?
No, unfortunately we didn't have the opportunity to do that at this time.
Actually, our RAND analysis would have, if we had to rerun the RAND analysis, we could have picked up on the fact that we would have built the plant several times, and we could have reduced the, You want to talk to that?
I don't know too much about that. Yeah.
Oh, okay. We didn't, but within the spreadsheet tool that we have, it does an analysis of new technologies and provides a number for increase in the capital cost and the operating cost due to technologies that are not mainstream. And so we could rerun those numbers and come up with another value that would apply a lot smaller factor to the capital cost estimation. Yeah. Okay. All right. Yeah. Okay.
The big ones were engineering issues and site development issues.
Okay, all right. So somebody else here has said that most of the big issues right now in our estimate that are causing risk in the capital cost are the site development and the methanol evaporator. What was the other one?
And the fact that we don't have any civil or electrical estimates.
Well, the civil and electrical is built into the factors. So, but we haven't looked at it in detail. Yeah, sure.
The only other thing I will add on to that is Chemicon had a bit of issue with actually getting with being okay with some of the sizes that we were recommending, especially for our heat exchangers, simply because a lot of the factors that it was using were based off of much larger equipment than what we wanted to design. So what that meant was the estimates that we're getting were being extrapolated as opposed to being on the curves that Chemicon was using, which meant that it's entirely possible that if we were to get an actual vendor quote for some of the shell and tube heat exchangers we wanted, they would be significantly less expensive than what Chemicon is telling us. So we would need to, essentially, we would need to be going to vendors for getting accurate quotes simply because the size of this plant is much smaller than any of the costing tools that we have is able to account for.
But we do have equipment quotes for the storage tanks.
Correct.
So, and that's a big chunk of the capital, right?
Yeah.
Yeah.
About 25%.
About 25% of the capital we have quotes for.
Yeah.
Any other questions
There you guys. Can you clarify the yield? I know the plants operating in China today typically use about 1.4 tons of methanol to make a ton of DME. What's the yield for the process that you developed?
82 divided by 632. Yeah, we had about 882. Oh, sorry, we had about 882 kilograms per hour of methanol flowing into this process and about 632.8 kilograms of DME flowing out. So that sounds like we're pretty, which is about a 72% yield overall for our entire process.
Keep asking tough questions.
Yeah, can I ask one?
Yes.
I'm just curious, did you look at how much production would have to come through the plant to break even? I mean, well, what I'm thinking of, you had a small scale plant that's running at a loss, but if we were just to increase the production just a little bit, would we ever achieve I'll call it a break-even operational position?
We did some preliminary looks at that, and Michael Bodley actually looked at a factor of applying about a 10 times factor. So if we were to scale everything up by about 10 times, we would begin seeing positive NPV values over the 20-year plant life cycle.
So, I mean, 10 times would be what annual production? I'm just
500 metric tons per year per truck, so 50,000 metric tons?
50,000, no, 500,000.
500,000 metric tons per year.
Interesting. So you're no longer a small plant.
Yeah. Can I ask a question? It's Greg.
Yes.
You chose the vapor phase high temperature alumina reaction as the scheme for your design. Why? Why did you pick that?
So there were a few factors that played into that. First of which was, at the time when the decision was made, it was deemed more safe to have a higher temperature but lower pressure process. But additionally, it came. Additionally, the higher temperature process required less unit operations for the overall. So that would reduce the capital cost. We essentially were trying to optimize capital cost to operating costs, and at the time, based on the very high level economic analysis, we had seen that the capital cost at that point would have outweighed the operating cost. Later on, it turned out that this wasn't the case, but at the time, we decided to move forward with the high temperature catalyst.
Did you, in the beginning, did you ever consider looking at reactive distillation to reduce capital costs and increase yield?
So, yes, we had looked into that, and it is a current recommendation. We had actually had some data from a few years ago from one of the other 470 projects that had looked into it, and at that point it was deemed unfeasible in addition to the economics, but also to the technical side of it, just because the current technology had deemed that reactive distillation columns was pretty advanced for making sure that they were running correctly. And so if we were trying to build a relatively small scale on a trucking depot, having the additional cost incurred for hiring the operators and training them, making sure that they were trained appropriately, would probably begin to outweigh the benefits.
Okay, thank you.
Plus, can I answer that too? We'd already done that a couple years ago, and we wanted to do something a little bit different. So it was a little bit arbitrary as well.
David Terry Switzer, you know Oberon's using a distillation column in California.
Yes, and we've been in touch with the consulting company, Unitel, that are doing the work for them through the summer. And we know they're doing some modifications to that process to try and make it more economical with external packed beds and things like that. So back when we developed this course, we actually had two processes that were competing with each other. I think the students kind of mentioned that. And one of the processes was a low temperature. We weren't looking at reactive distillation, but it was essentially the same catalyst that Unitel are using. And then this gamma aluminum catalyst. And so we kind of chose about halfway through the course to just pursue one of the options.
And just another comment, your cost estimates, as it turns out, very close to what Oberon is quoting for their small-scale plant, which is about the same size.
Well, that's good.
Can you just clarify what those costs are? I didn't quite get that from the PowerPoint. Like, how many tons of DME does it produce, and what's the total capital, and how much of that is labor?
How's the operational cost breakdown?
In terms of capital cost.
Oh, there it is. Capital cost was
5.9, about 5.9 million.
So yeah, so the initial capital that Chemicon was giving us was approximately $5.6 million. But when we applied the RAND cost growth, taking into account some of the newer unit operations that we had designed and some of the factors that we hadn't taken into account, it actually inflated up to about 7.5 million, simply because based on past experiences for some process plants, the RAND company was able to put together this model. For cost.
How many tons of DME is that per year or per day?
500 a year.
Yeah, so it's 500 a year.
Metric tons. Metric tons, yeah.
500.
No, 500 metric tons per year. 5,000. Oh, sorry, 5,000.
Yeah, sorry, 5,000 metric tons per year of DME.
Okay, that makes sense. Okay, thanks.
Yeah.
Any other easy questions?
And just to clarify, the diesel price that made this uneconomical was how much?
We had looked up about $1.21 per liter. And correct. That was the most recent number reported for the Kingston area as of November 20th, I think. But we did run a second analysis, and it was deemed that assuming that we were able to get a long-term contract without changing price of methanol from that $475 per metric ton, the diesel price would need to go up to about $2.30 per kilogram to make this project feasible.
Do you know what that is a liter? No. Sorry.
It's, well, they're, what, 840 grams in a liter?
Right.
Yeah. So, You can do the conversion in your head, right? You're engineers.
Yeah. Oh, we need a lawyer for that. Okay, any other questions? Sounds like there's no more questions.
So actually, let me just comment. It's a good model. It's very instructive if we want to move forward on a demonstration like Oberon's doing in California.
Thank you.
Thank you very much, guys. Well done.
Thank you.
Thank you very much.
Thanks a lot.
I just want to show you guys one thing here. I'm not sure whether I can do this or not. This may, we may lose the connection here. Let me try.
And I'm going to pull that out. Okay, let's see. Are you guys still there? I think they are. Okay, I just want to show you what chemical engineers can also do, which is to make periodic tables with cupcakes. Anyway, we're about to eat all those cupcakes. Okay, thank you very much, and I will be in touch.
Okay. Bye.